So, well, I'll just get set up here. Are there any questions from either the lecture or anything else? Okay. So can everyone hear me all right first? Cool. So then, I did not tube. Did you just send that? Oh, yes, no, I apologize, I did. Yeah, so I reached out to the College of Science, and I need to figure out kind of what's going on there. We can talk about it privately if you want to, but yeah. So both myself and Rajab are trying to figure that out. Yeah, I'm sorry that I didn't get back to you until now, and part of it's yeah. there's a lot of not knowing what's going on with visa issues at the moment. So I really apologize though. Yeah, which is also to say, so with the announcement yesterday, I think that you should basically expect that Northeastern is going to continue on as we were planning. So just don't, those of you, so I sent out, I should have sent out information to everybody. If you did not get an email from me containing basically what the current university policy was within the last few days, let me know. That means that we don't have your current email address. But basically, as far as it has been worked out, it seems like if you cannot get a visa to come to the US, then you can still attend classes online through NUFlex effectively as if it was an on-ground degree. You can also defer, and I have a question out to OGS about when the last date to defer technically is. So you can also defer for a semester, but as far as I know, if you're not able to get a visa, then the situation basically you can take classes through NUFlex, and it seems like that is supposed to be as if you were taking a normal on-ground class credit-wise. If you are here, then you will have to take at least one on-ground class. There's a lot of debate about what that means. For us, it's probably just going to mean that you show up and the person teaches. But there are, of course, some professors and some students that don't want to come to campus. Northeastern's put in some pretty effective social distancing measures for campus. And there's a lot of different things that these on-ground classes are going to look like. So some of them are just going to be standard lecture classes. Some of them are going to basically have like a homework session or something that you can attend with the TA, and that counts as the on-ground component. You know, sort of no matter what it is, it's just supposed to be a sort of like, you know, yes, you are actually here in Boston. That's the upshot. And I would expect that you should expect that, even given that the administration has gone back on the executive order, just because I think that will still probably be, that will still happen at Northeastern either way. But also I would just, nothing more severe than that is going to be the case. And so I would just hold that as the standard, you know, as this all shakes out. But yeah, if you have individual questions, please do let me know. And I'm kind of trying to get answers out of OGS and out of the College of Science as much as I can. Yeah, so, and I apologize that it's being so slow. But does anyone else have any questions? Assignment, is it x1 prime and x2 prime? Oh, it almost certainly is. Yeah, if I said something else, I'd have to bring it up quickly. If you ask that question on the forum, I will answer it there, and then everyone can see the answer. But we'll go over that today as well. Okay. Yes, yeah, sorry. It should be, yeah, it should be x1 prime, x2 prime, x1 prime, x2 prime, x1 prime, x2 prime. And yeah, so yeah, we'll go over that a little bit later today. Okay. So let's get started. Okay. And again, let's make sure that everyone can actually see what I'm writing here. Okay. So what we want to do today So we're going to start by summarizing the information that we kind of derived last time about these simple homogeneous first order systems of linear differential equations with constant coefficients. And then we're going to start talking about our kind of first examples of systems as they're applied to modeling. So we're going to talk about some biokinetic models, which actually are linear and are quite widely used, and where the challenge there is not so much doing anything difficult mathematically, that the challenge winds up being the fact that you have a huge family of models that you can fit to things, and people are kind of trying to discover what the best ones are. And then we're going to talk about the SIR model, and we'll define that and show how to use it, or show the sort of the basic pieces of information that you can extract from it. And then I think that we should get at least a little bit into phase plane analysis. But if not, either way, we'll break with about an hour left and go and look at the homework and go through that first or that second Jupyter notebook. So out of curiosity, how many of you have taken a look at the Jupyter notebook yet? Currently, we at least have one, at least on How Has. Cool. So hopefully, yeah, so hopefully it seems like it's relatively straightforward after the first one. So it shouldn't take too long to go through, but I do want to take a second and discuss the assignment at the end. And if any of you have looked at it enough that you have thought about the assignment at all, I would encourage you to ask any questions that you have. Okay. So let's start with how we finished. Classification. Systems of homogeneous say, of first order. Homogeneous differential equations with constant coefficients. Okay, so given, as a sort of formal statement, so given x in, given x equals x1, x2, and a 2x2 matrix, with, and we're just going to, yeah, a 2x2 matrix with a basis of eigenvectors. Basis of eigenvectors. Two eigenvalues, lambda 1, lambda 2, we had the following classification. Classification of the solutions to x prime equals ax. So if you recall, we had sort of two large families. So on one hand, we have lambda 1, lambda 2 real. And again, if one of them is real, the other one has to be because they have to come in complex conjugate pairs. Then if lambda 1, lambda 2 are less than 0, so this is the rough classification, then all solutions limit to the origin. We also had that, so if lambda 1 is less than 0 is less than lambda 2, then in this case we had our saddle. So this is a semi-stable node or, yeah, semi-stable node or saddle. And all solutions to infinity, sort of in formal sense, along V2. And our third case, where we have lambda 1 0 is less than lambda 1, lambda 2, then this is our unstable case. Unstable node. And all the solutions, again, are going to limit to, you know, some unbounded infinity. Okay. So any questions before moving on to the other set of cases? So we had another set of cases, right? So this is what happens if we have real solutions. It's possible that we don't have real solutions, right? So it's possible that lambda 1 and lambda 2 are complex. But I actually, by complex, I want to sort of say like really complex, right? Like not, you know, real numbers are of course a subset of the complex numbers. So if these are in the complex numbers minus the real numbers, non-real solutions. Then first, we know that lambda 1 is equal to lambda 2 bar. And then V1 is equal to V2 bar, so complex conjugate. And then so if we write lambda 1, I'm just going to write this as lambda from now on, is A plus IB. Then the first thing that we find is that solutions are of the following form. The form xi is some constant times e to the at. Actually, write this in a slightly nicer form. These look like e to the at times some constant some constant times cosine bt plus some other constant times sine bt. So this is the rough form. So each of our equations is going to look like a product of something in sine and cosine and an exponential. And the period is going to be given by the imaginary part of the eigenvalue, and the decay factor, the decay, or the overall decay is going to be given by the real part. And so we have the following behavior. So we have, if A is less than 0, then we wind up with a spiral towards the origin. Whoops, whoa. A is less than 0. Spiral, well, wait, sorry. Then this is what's called a stable focus. And the solutions spirals towards the origin. If alpha is greater than 0, then of course we have an unstable focus and things spiral out away. So unstable focus. And solutions spiral away from the origin. And finally, when alpha is actually 0 and we have a purely, sorry, change from A to alpha here. We actually have a purely imaginary solution, then that's where we wind up with the case of the closed circular orbits. So here, this is closed circular. It's around 0, 0. Okay, any questions? So then the last thing, so we want to keep all these behaviors kind of in mind, because this is really sort of all that can happen. And in particular, so you can get cases where when you have larger numbers of eigenvalues and eigenvectors, where, for instance, you know, you'll get sort of similar behavior to this. So, you know, if you have real eigenvalues and all of the eigenvalues are less than 0, then you're going to have a stable node. If all of them are greater than 0, then you have an unstable node. Usually you have a semi-stable node, so some of the eigenvector directions will be pulling things in towards 0, and some of them will be pushing them out towards infinity. You can also get fun cases where, for instance, 2 of your directions are complex and the other one's real. And so what you get is spiraling solutions that spiral in a plane, you know, outwards along the orthogonal eigenvector. And so there's all kinds of really beautiful behavior that you can get in higher dimensions, but it's all kind of built out of these component pieces. And there was what we finished on last time was the trace determinant plane. I want to go over that a little bit, just a little bit more clearly, since I rushed it a bit. But the idea is that, oops. It turns out, so again, a lot of our job in mathematical modeling is trying to summarize information in a usable and digestible way, especially complex information. So for instance, in this case, we just noticed that the determinant of A minus lambda I, so we're trying to find the eigenvalues, right? So here, this is what this classification has given us is basically a lot of information about the behavior entirely in terms of the eigenvalues, which are relatively easy to compute, even for large systems. Relatively easy to compute and easy to understand. So what do we get? Well, it turns out this is let me not double count my A's here. A1, A12, A21, A22. So this is A11 plus A22 plus A11, A22 minus A21, A12. And we noticed that this is lambda squared minus lambda times t lambda minus d, where t is the trace and d is the determinant. And then so solving, the eigenvalues then are given by t plus or minus square root of t squared minus 4d over 2. And so then basically in analyzing this, this quantity t squared minus 4d over 2 we'll call delta. And the positivity of this quantity is what determines whether or not the solutions are complex or real, right? So if this guy's positive, then the square root exists in the real numbers. And So the solutions are real. If it's negative, then we have complex solutions. And so then the picture is so if we have the trace and we have the determinant and we have the line delta equals 0, which will be a parabola, right? It'll actually just be, you know, d equals t squared over 4. Then if we're on the north side of this line, if we're above the line, then this is then the determinant, 4 times the determinant is larger than the trace squared. And in fact here, so this is less than 0, this is greater than 0, and we're going to get up here are going to be our complex spiraling solutions. And so the next determination, so we have complex solutions, and eigs. So then our next determination, we're kind of trying to summarize all this information in one picture. So quick question. So if I have complex eigenvalues and t is greater than 0, then is this a stable focus or a stable node? So given this equation, given this solution, right? If I have complex eigenvalues and t is greater than 0, then are the solutions over here, are the solutions over here stable or unstable focuses? Sure, why? Yeah, so everyone's correct. Yeah, so it's going to be stable, right? Because lambda, of course, is going to be the alpha for lambda is going to be, or so the A for lambda is going to be t. And so, oh, sorry. I said correct, it's actually the other way. So in this case, so the real part here is going to be t. And so if the real part, which is A, is greater than 0, we're actually in the case of an unstable focus. So we should be so this is where things will spiral outwards. And so then similarly, if t is negative, then in this case, the real part of the eigenvalue is also negative. And so then the coefficient of coefficient of t in the exponent will be negative, and we'll have stable focuses. Any questions about that? Okay, so in thinking about this, if we go down, so in this region here, so this is where, okay, so we're in real solutions, but t is greater than 0. What would we expect to happen So complex eigs, so down here we have, I should say, so here we have our real eigenvalues. So if the eigenvalues are real, but t is positive. So eigenvalues are real, t is positive and greater than 0. Sorry, t is positive, and the determinant is greater than 0. Then what do we expect? Are we going to have stable solutions or unstable solutions? So in this world here, right, so t is greater than 0, d is greater than 0. Yeah, exactly. So we're going to have unstable nodes. With our sort of rough picture of solutions going outwards in all directions. Right, and roughly the reason for this, right, is okay, if t is greater than 0, then t is greater than 0. It's of course, so if we take something positive and we add something positive to it, we're always going to get something positive. There's of course some concern that when we subtract off this this tail here, that we're going to get something negative. But since d is greater than 0, whatever delta, capital delta here, that's the triangle, capital delta is actually less than t, right? So here, delta is less than t, so the two solutions are both positive. Delta is less than t, so lambda 1, lambda 2 are greater than 0. So similarly, if we're over here, so we have t, sorry, less than 0, d greater than 0, and delta greater than 0, then we're kind of in this other case where delta is less than t in absolute value. Then delta is less than t in absolute value, and so, okay, it doesn't matter when what we add to it. Sorry, I should say delta is less than t squared. Delta is less than t squared than t squared still, so there's no way, so we have the solutions are negative, and if we add delta to them, it doesn't bring them back to being positive. So we're going to have stable nodes. And then what's the last case? So we've summarized most of our information here. Semi-stable, exactly. And where is that going to live? Where will we find, where on this graph will we find semi-stable solutions? Under the t-axis, exactly. So down here, this is where we've got delta greater than 0. We've got, actually, doesn't matter what t is. D is less than 0. And in this case, what this means is that delta is actually greater than t squared, which means that whether t is positive or negative, when we add delta onto it, or we add the square root of delta onto it, one of the solutions will be positive, the other solution will be negative, and we get semi-stable. And these are my favorite. Okay, so here's our classification of, this is our classification of solutions to this kind of equation, which will very quickly turn into our classification of fixed points in equilibrium solutions for nonlinear systems. So before we move on, are there any questions? And the final, are there any questions? And is there any potential interest in seeing one last example here? Okay. Is semi-stable nodes? Yeah, so for semi-stable nodes, the eigenvalues will be real. In fact, in this picture, I mean, this is sort of a funnily distorted picture in some ways, because all of the complex eigenvalues live above the parabola, which, you know, there's in some sense more complex eigenvalues than there are real eigenvalues. So the space for the real eigenvalues on this picture actually takes up more space than for the complex eigenvalues. But yeah, for semi-stable nodes, the eigenvalues will be real. Any other questions? Okay, so there's a bunch of practice problems. I've also posted some resources on how to do these computations. If you have any questions about them, please let me know. And I'm more than happy to go through them. But if you haven't done these computations before, you know, I would just get some practice, you know, drawing out these solutions and seeing what you get. And then once we introduce the numerical solutions today, you know, just get some practice playing around with them. Okay. So let's look at a modeling example. I can't spell pharma. So pharmacokinetic models. So the basic idea here is that we want to understand things like drug transport throughout the body. Drug transport is a simple example. Things like iron transport, other, you know, biological compounds are also common to understand in general how chemicals move through the body. Drugs, nutrients, you know, neurotransmitters. So we want to understand how these things move through the body. And the way that these models exist in industry right now, people actually spend quite a bit of time in where there's a part of computational biology that spends quite a bit of time doing this kind of stuff. There was actually, it's a interesting role if you have any interest in this with a background in mathematics, that you can jump into sort of the computational side of this. I actually almost got recruited out of my PhD by a lab that was working on trying to construct these models, because the basic idea is if we can figure out, if we can get good models for how chemicals move through the body, then all of a sudden we can start pulling information out of it, right? So for instance, what kind of dosage you should give patients with certain parameters and attributes, how you can check what, how much of a certain drug is within the brain or something from, blood information if you have a good enough model. So there's a lot of people trying to work this out, and there's quite a few off-the-shelf models you can sort of buy, but a lot of them are based off of a couple of really basic principles. And these are essentially principles that are going to wind up looking a lot like our mass flow models. And mass flow, of course, is one of them, right? In some sense, the first component of this is actually to think about things as salt tank models. So you have two liquid systems, and you've got some drug in one, and it's flowing into the other. At the very most basic sense, you can try to figure out how the drug transfers between these two pools. So let's look at drug transport in a simple system. So here we have some drug. Is absorbed. At site A, moves to the bloodstream. B, and then gets expelled. Gets expelled to E. And so by abusive notation, I'm going to refer to A, B, and E as the amounts of the drug in each of these systems. Notation. A of T, B of T, and E of T be amounts in each system, and let VA, VB, VE be the volumes of each system. VE be the respective volumes. Okay, so if we want to draw a picture of this, this is of course going to be some nice box model. So we have A, B, and E. And in general, for a mass flow model, of course, this would just be some rate of flow in between. But we want to now go through and specify a slightly different mechanism, right? Because it turns out that, like, if you take a pill and you put it and it goes into your stomach doesn't just flow into your bloodstream, right? The actual mechanism by which it happens is an absorption mechanism. And this will be very common, right? And basically, when we construct mathematical models using differential equations and using these box models in particular, usually what we do is we create our pools, our quantities, and then we just need to specify the medium of transfer. And we just need to construct carefully what the rules are for each medium of transfer. Okay, are there any questions so far? Just about the kind of the setup here. Okay. So basically, this is one picture of how absorption could work. So of course, this model can be significantly complicated, but for a simple picture. So the basic idea is that we have some permeable membrane. So I should say a semi-permeable membrane. In fact, what is sort of a better cartoon picture of it is something like this. So basically, we've got fluid on one side. We've got volume A. I shouldn't say volume, let's say fluid A. We've got fluid B. And inside the fluids, we have the actual mass of particles. So this is the drug. And we assume that the drug is moving around basically using Brownian motion, stochastically. So drug is moving randomly. So these guys might be going this way, and these guys might be going this way, and these guys might be going this way, and these guys might be going this way, right? Every now and then, one actually gets close and is going the right direction and pops out on the other side. Because it's a semi-permeable membrane, we're going to assume that we can only transfer it one way. And so we'll have some particles on this side as well. Okay, so we want to figure out then, how do we actually compute, or how do we give some sort of kinetic picture, some like large scale kinetic picture for the small scale phenomena? Of course, we could, we could go and just do a simulation, and assign things, or we could, try to think about this in a probabilistic sense. But here is one way to make this picture a little bit more, or to try to pull sort of a high level picture out of this very low level picture. So let's assume, actually, sorry, are there any questions though? Is this intelligible so far? Are there any questions about what I've drawn? Okay. So let's make two assumptions. Assume the only, so for some time interval, interval delta t, the only drugs that have a possibility of randomly going through are in some small volume around the membrane. Within delta V of the membrane. All right. So let's say that we have, so it's only the guys that are within this area that even have a chance of jumping through the membrane within a certain time interval. And so, I mean, this, of course, there's other ways that this gets cashed out. For me, I just like to think about things probabilistically when I'm thinking about differential equations. It seems to be this sort of particle to high level. It's the easiest way for me to think about things. So that's what we're going to do as well. Okay, so further, let's assume that each particle in the delta V volume has a p chance of passing through. Okay. So then what we want to say, right, is, so then how is the mass changing? So we could talk about concentration, but I want to talk about mass here. So dm dt, so we're losing mass. Okay, we can only, basically, we kind of want to think about how many particles is it possible for us to lose. Okay, so we can only lose particles within the volume, right? So how many particles are in the volume? Well, so given, so this would be delta V times the concentration. Actually, let me be a little more careful. MA over VA. Okay, so this is the number of particles we have in the volume. And then P is the percentage chance that a particle within the volume, so that's sufficiently close to the membrane, will actually cross over. So this is number of particles close to the membrane, times P, the probability of crossing the membrane. So we would assume then in any time step, and if we want to make this a little bit more precise, we could of course do this out, you know, with the delta t, so with the delta t, and then take the limit and blah, blah, blah. But it's basically that part of the calculation is the same as what we did on the first day. So this is going to be then my proposed mechanism, or dma dt is equal to minus k times the concentration, which we can also say is minus k times m over v. Okay, so are there any questions? Or actually, sorry. Yeah, no, that's fine. All right, are there any questions? So in particular, and this is important, this is a constant coefficient. So this is exactly the kind of equation that we've been talking about and constructing. All right. Okay, so are there any questions about this setup? Does this make sense? Do you believe me? Do you have addendums or questions or things that you'd want to add to it? Oh, MA, thank you. MA is the mass of drug in system A. That is an omission on my part. Thank you. So just to confirm, so MA over V, not quite. So yeah, so MA over V times delta V is going to be the number of particles, right? Because MA over V is the concentration, right? So technically this is the concentration. And so, yeah, so MA over V is the concentration. So then if we want to know how many particles are actually in that delta V volume, it'll be the concentration times delta V. So MA over V times delta V in this case. Yeah. Any other questions? This is kind of like a non-trivial setup. So all these are good. Okay. But yeah, so there's this kind of fascinating upshot. So there's a little bit of a complicated picture. I mean, at the end of the day, you know, if you squint, you can see the similarities with the other pictures that we've drawn, right? You know, we're basically assuming that there is some threshold, that you have a probability of crossing, and then you're out of the system. And that probability then is going to mean that we just have some like nice linear constant coefficient equation. So I apologize, I'm gonna change this. I'm gonna say that this is this is going to simplify our notation drastically in just a second. Minus K times M A, which we note is minus Ka times the concentration times the volume. Okay. So now we want to take this formula basically and place it on each of these arrows for the rate. We want to use this. For the rates above. In ABE. So what does this mean? Okay, so we start in the absorption site. We'll assume that we'll just assume that that whatever the drug is instantly absorbed into A. So then basically what that means is that the initial concentration of the drug will be given as an initial condition. It's not a rate that we have to put in. We could certainly put it in as a rate, right? So for instance, if you had a pill that you took and put in the stomach, we could include that as a rate. There's an exercise on that. But for now, let's assume the drug is immediately absorbed into A. To A. So the equations become we're going to have dA dt. So here's where I'm going to abuse notation. I can make it m sub A if it's helpful, but is going to be, well, okay, so we've got some rate coming out. So minus K1 A. Yeah, sorry. Let me stick with what I've established, with what I established a second ago. Silly to change now. MA. B. Okay, so we've got a certain amount of mass coming out of system A. It's being absorbed through by conservation of mass. Can't go anywhere, so the amount that comes in has to be M1 times MA. And then let's assume that the same mechanism happens to absorb from the bloodstream to whatever excretionary mechanism we're using, so kidneys, etc. So this will be A2 MB. This is just going to be A2MB. So we can see what's going to happen here exactly, right? We absorb through the absorption site. We absorb through the absorption site. We then, it sits in the bloodstream for a while, but immediately starts being absorbed through the kidneys or whatever our excretionary mechanism is, and then it eventually will all pool in the excretionary mechanism. And this is a nice linear system. It's a linear first order homogeneous system with constant coefficients. Okay, any questions about how I wrote down these equations given the considerations above? Okay, so given this, let's solve. Oh, can you say one more time how we got ME? Oh, yeah, so basically, I'm just assuming, yeah, I think I didn't say that much about that. Okay. Yeah, sorry, a couple questions. Let me start at the top. Routing was asking, so what is K? Yeah, so K here is the same as the KA up here. So it's going to be some combination, so it's going to be highly dependent, right? It's going to be some combination of whatever our delta V is, whatever the probability is within that volume. And so it's going to be dependent on the system, but essentially it's going to be the rate of transfer of the drug across the membrane is roughly what Ka is. So is roughly what each of these Ks are. So here we're assuming that, like, for instance, you've taken a pill, it's being absorbed through the gut or through the intestine, and so it's crossing some membrane through some mechanism like this, some semi-permeable membrane. There's similar equations for other kinds of mechanisms of osmosis. And then, yeah, and so that's that, and K is the factor that determines that rate, right? And secretly, Ka is, I should actually say that here. Thank you. Ka secretly, right, is delta V times P over VA. So it depends on a lot of things. And in this case, of course, it additionally depends on our assumption that the volume is actually constant, right? It is entirely possible that, with your bloodstream, the volume's usually pretty constant unless something's gone horribly wrong. With your stomach, though, of course, the volume may not be constant. So we're making another assumption here, which is the volume is constant. Cool. And thank you. I didn't actually write that down anywhere. So is this K2MB? Yes, that is correct. Yeah. So, and I think that you may have written that when I had written down the wrong thing before. Yeah. So the rate of change for the mass in the excretionary system is the same. Again, this is just by conservation of mass. If we have any mass leaving the bloodstream, it has to go somewhere. Where does it go? Into the excretionary system. And the last question, yeah. So then, how do we get this equation? Basically, we get this equation by we're stipulating that this mechanism is how all of the mass transfer works. So it's mass transfer from the bloodstream, from the absorption site into the bloodstream, and it's also the mass transfer from the bloodstream into the excretionary system, either through the kidneys or the liver, something like that. So, any other questions? Okay. Yeah, and do keep them coming if you have them. Okay, so let's solve this. We know how to do this now. So in order to solve this, well, we just need to find the eigenvalues and the eigenvectors. So this is basically m prime equals am for a equals minus k1, 0, 0, k1 minus k2, 0, and 0, k2, 0. So a relatively sparse matrix, which means that we have some chance of actually finding the eigenvalues here without a computer. And we can write them down. So this isn't actually not hard to do. Eigenvalues. So this is going to be the determinant of A minus lambda I, which we all remember how to take three-dimensional determinants. This will be the determinant of minus k1 minus lambda, 0, 0, minus k2 minus lambda, 0, 0, k2 lambda. And so multiplying things together, what are we going to get? Well, okay, so the determinant here is actually really simple because it's just going to be lambda plus k1, lambda plus k2 times lambda. Okay. Right, it's this times this minor, then 0 times the minor, 0 times the minor, all both of those are going to be 0, and in this case it's going to be this times the minor, which is just bam, okay. The other way to notice is that this is lower triangular, so that has to happen. Floor triangular. Oh, it absolutely is minus lambda. Thank you. And that whole thing should have an overall sign. Thank you very much. Yeah. So thank you for everyone who caught me on that. So the eigenvalues are going to be lambda 1 equals minus k1, lambda 2 equals minus k2, and lambda 3 equals 0. So we haven't really talked about what happens when we have a 0 eigenvalue. But in fact, the case doesn't change at all, right? Quick question. So a quick poll. What is going to be the result of having a 0 eigenvalue in the final equation? So the determinant is certainly going to be 0. But that's okay, right? And that kind of gives you a hint. That tells you maybe what's going to happen for the final system. Now, think about it. We will see what happens here. Okay. So I can just write the eigenvectors down. Is there any interest from anyone in seeing me derive the eigenvectors here? It's not a super complicated equation, but I'm more than happy to do it if there is interest. Okay, sure. So for lambda 1, we're going to get so a minus lambda 1 times I times v equals 0. We're going to get an augmented system. This is the way that I'm going to do it. So minus k1. So if we add k1 to everything here, we're going to get 0, 0, 0, k1. We're going to get minus negative, and so this is going to be k1 minus k2, 0, 0, k2. K1. Oops. Let me actually write this as an augmented system. And so, I mean, we can kind of back solve this, or we can actually kind of just stop here and, and write down the equations. And I'm actually going to go for that in this case. I mean, this is sort of it's going to wind up being faster to do that than to back solve. So what do we get? So here we're going to say, let's call these variables x1, x2, and x3. So what are we going to get? We're going to get that x1 times k1 plus k2, x2 is equal to 0, or x1 is equal to, I almost certainly want to do it the other way. X2 is, k1, x1 divided by k1 minus k2. Great. Second equation. The third equation here is going to give us K2 times X2 plus K1. So X3 is equal to carefully so this we can write as K1 times K2 over K1 minus K2 X1 K1 X3. So this is going to give us that X3 is equal to K2 over K2 X1. So those are two equations. So we've got two equations, three unknowns. This is exactly what we'd expect. We expect a one parameter family of solutions. It's an eigenvector. So we're going to have V1 is equal to, I need to be a little bit bigger, but X1 times K1 over K1 minus K2 X1 times K2 over K1 minus K2 X1. And we get to pick, oh, did I make a mistake? K2 equals K1. Yes, you are absolutely correct. Yeah. You're absolutely correct, and actually I like the way that you put it there. Sorry, I forgot a minus sign. Fabulous. Yes, thank you to Don Howe here, saving me mathematically. And then inevitably I will have forgotten a minus sign on the other one too. K2 minus K1, but I forgot a minus sign twice on the third one, so the third one's okay. Okay, so, thank you. Now let's just pick X1 to make our lives easier. So pick X1 equals K1 minus K2. It's easier to deal with things that aren't fractions. Let me actually put that down there. So technically this is for any X1 in R. So X1 equal to K1 minus K2, and we get V1 equals K1 minus K2 minus K1, K2. Okay, any questions? All right, so that was a little bit of work. It turns out the other two are really simple. For lambda 2 equals minus K2, we get A minus lambda 2I times B equals 0 is going to give us the augmented system, what, minus K1, K2, K1, 0, 0, K2, not 0. Which, with a little bit of work, you can quickly see that this is just going to be, so, okay, well, writing it out in equations, we have the equations explicitly. X1 times K1 equals minus K1 plus K2 times X1 equals 0. Great, done. And K2 X2 plus K3, sorry, K2 X3 equals 0. So the solution is, well, this is only solved if X1 equals 0. Great. This is only solved, well, okay, K2, K2, so this is just, we can pick our favorite, minus 1, 1. Any questions about either of these computations? Okay. And then finally, I'll just state it. So for lambda 3 equals 0, well, the augmented system in this case is just the original matrix, right? And so you can see what it's going to have to be. It's going to be 0, 0, 1. 3 equals 0, 0, 1. Okay. So I'm going to, okay. Now we can just solve this. So we have our eigenvectors are only sort of complicated. Oh, we actually have them all in this frame even. So the only sort of complicated one's the first one. In fact, sort of interestingly enough, all of the parameter dependence comes through the first one as well. Somehow these other two eigenvectors are completely independent of the parameters themselves. And so let's see what happens. So we're going to get m equals C1 times e to minus K1t times V1 plus C2 e to the minus K2t V2 plus C3 e to the, well, okay, e to the eigenvalue here is just 0, right? The eigenvalue is 0, so e to the 0 is just 1. And so that's what happens when you get a 0 eigenvalue, is you'll wind up with constant solution, or you'll wind up with a constant term here. And this is kind of good, actually. We'll see that this is actually what we should expect to get in just a second. So writing this out in coordinates, though, this will be MA is equal to C. Okay, so we just fill out the eigenvectors, right? So we have K1 minus K2 here, and we've got no first component in either one otherwise. So I've got K1 minus K2 minus K1t. Our formula for the bloodstream then is going to be minus C1 minus C1 K1 e to the minus K1t plus C2 times, minus C2. So minus 1 times C2 times e to the minus K2t. And then again, we've got a 0 here in V3, so there's no term. And then finally, ME is going to be C1 times K2 e to the minus K1t plus C2 times 1 e to the K minus K2t plus C3 times 1 times, well, e to the 1, so 0. Great. Okay, so quickly, I argue this is exactly what we're supposed to get. because let's think about how we have it set up. We start with a bunch of mass in the absorption site. It is that the excretion site, so what will happen asymptotically in the system, right, is that eventually, I'm being told my internet connection might be unstable, so let me know if something goes wrong. But so what we should expect to happen here is that everything will wind up, everything will eventually wind up in the excretion oratory system, right? And what that means is that basically, asymptotically, ME should just be constant, right? It should end up with all of the drug in there. And that's what we're seeing. We've got some constant term, and we've got some exponentially decaying terms. And so this is so that at least is exactly what we would expect. We can actually, so I'm not going to solve out the coefficients for you. It's not too hard to show. So, but if MA is equal to, let's call it the initial mass M naught, and MB is equal to E equals 0, then we get the following. So we get MA is actually M naught E to the minus K1T. MB, it turns out to take on this kind of nice form, equals K1 minus K2 times E to the minus K1T minus E to the minus K2T. So we can see the absorbing term and the taking away term in a way that wasn't so clear a second ago. And finally, we get M naught over K1 minus K2 times K2 e to the minus K1T minus K1 e to the minus K2T plus M naught, which again, I argue is exactly what we would expect, right? We get some exponentially decaying. So at time t equals 0, we see that all of the mass is going to be in system A. But then for the long range, all of these decay out, and we eventually wind up with the mass in system B. Sorry, in system E. MA equals MB equals 0. Okay. Any questions? Okay, so one thing that's useful about these kinds of equations that's not quite the right thing to say. So, okay, so this is a great example because we can actually solve the whole thing out explicitly and get a formula, right? So then if you're actually working biokinetics, your job, or sorry, pharmacokinetics, your job becomes how do you determine these K? So scientist job, how to determine K1 and K2. And that involves going out and doing a bunch of experiments, and K1, K2, of course, will inevitably some sort of compound factor of, you know, the person's metabolism, their blood sugar level, their how much they've eaten, you know, all kinds of stuff. But the hope is that if you can fix those, then you can wind up with a viable model. And so there's another thing, we're going to talk a lot in the next couple of weeks about extracting information from models that when we can't actually solve them. And to just give a quick example of that, So the solutions are good. Solutions are good. But let's look at an example. Example of actually extracting something from the model. So here's a question. When is MB at its maximum? Okay, so this question, of course, like, and so sorry, I think I'm going to go for a little bit longer, finish out this part of the lecture, and then we'll break, and then we'll do the lab. Okay, so we can actually figure this out pretty explicitly from the formulas here, right? We just take the derivative, we set it equal to 0, and we get, you know, some formula. But so there's a way that we can say something about this without actually having to go directly to the solution. Without solving, we can still get useful information. So namely, if we want to know where MB is at its maximum, let's take a look at the original equation that we had, right? We had dMB dt equals K1A minus K2B. Oh, sorry, MAMB. So in particular, we know that this is going to be, so initially, MA is larger than MB. Well, in particular, it doesn't matter because MB is 0, so initially K1 MA is larger than K2 MB. So MB prime is positive and MB is increasing. Eventually it flips. Eventually, so as we drain everything out of the absorption site, we're going to have that K1 MA is less than K2 MB. So M prime B is less than 0, MB is decreasing. Okay, so if MA is increasing initially and then it is decreasing, what does that mean that we have to have a critical point? Or sorry, that if we can find a critical point, sorry, let me be precise. That means that there must be a maximum between the two. Must have a local max at m prime b equals 0. Ah, okay, that's brilliant, because we can then cash this out. So when 0 equals k1 times ma minus k2 times mb, and so we have a formula. So mb equals k1 over k2 times ma. When this occurs, we have a critical, so there's only well, yeah. Okay, I know that there's only a single maximum, but this is potentially a quantity we can measure live. We can measure. And so in particular, this allows us to get a handle, so one of the big questions, of course, is how do we estimate things like, so how to estimate K1 and K2. Well, so one straightforward way is to, so maybe, it might be hard to measure things in the liver, but we can try to measure K1 and K2 by monitoring these quantities and finding something like the maximum, and then relating the maximum, the maximum concentration or the maximum amount of the bloodstream to the amount that's in the stomach at that time, right, or within the absorption space in that time. Okay, so of course, in this case, as I said, we can go and actually get a really solid idea of what the maximum actually is. And we could even fit pretty closely what these rates are if we really think that this works. But this is a really useful thing, to be able to look at these differential equations themselves and extract these kinds of relationships and formulas, just because often we can't actually solve the things. And there's a lot, but also there's a lot of hidden information within the differential equations that maybe isn't so clear by looking at this, right? It turns out if you take the derivative, you can of course rederive this formula without too much trouble. But this formula just falls out, immediately from the equations. And again, this is a formula in terms of quantities that are the actual quantities that when we go out into the world, we're measuring, right? And so we can use formulas like this, hopefully, to kind of detect hidden information about the parameters of our system. Okay, any questions? All right, so I had another example, but I want to get onto the SIR model since you guys will be doing that in the lab. Yeah. Oh, but I would say, yeah. So if you're interested in pharmacokinetics at all, what the game here is of course to not do this with 3 simple systems, but to really say okay, we've got the heart, we've got the liver, we've got the bloodstream, we've got the blood-brain barrier, we've got the kidneys, we've got all of these systems. How do we set up this large system of differential equations with all of these parameters relating them through these different transport mechanisms? And then how do we fit those, and how do we do this carefully? It's quite an interesting little field right now. Okay. So let's take a look at, so this is what's known as the SIR model of infection. SIR model of infection, or I should say of disease spread. Okay, so let's consider three populations. So we have S is our susceptible I'm just going to go ahead and spell check that because I know I spelled that wrong. Wow, this may be the first time in my life I have spelled susceptible correctly on my first try. So. We also have an infected population. And a recovered population. So you could, of course, include lots of other different kinds of populations. You could include a dead population, an immune population, all kinds of things. This model, I mean, the model that I'm going to spin out here isn't even as, it was even more complicated in the first paper that it appeared. But this forms the basis for just about every epidemiological model that we have right now. I shouldn't say it, for many of the epidemiological models we have right now. So the idea of contact here, so is the following. So we've got susceptible moves to infected, moves to recovered. And so susceptible moves to infected, moves to recovered. And the mechanism of infection here, we're just going to assume is completely random contact. It's random contact. So the idea here is going to be that there is a certain percentage chance that any two random members of the population meet each other. Okay. So that's one probability. And then there's also going to be a probability that if two random members of the population meet each other and one's infected, that the infection is transferred. So that's what's called, so the C, chance of transfer of infection. Okay, so quick question. Given this, I'm going to propose that ds dt, so the number of susceptible people is going to be proportional, so we're going to be losing susceptible people at the rate at which they get sick. What am I going to propose, given these two probabilities, for the rate at which the susceptible population decreases? So it's going to be minus PC. We're going to need some other terms though. So it's absolutely correct. That's going to be minus PC. And then what else do we have to multiply it by? So this is the chance that that an infected person meets a susceptible person. Okay, close, right? So you're absolutely correct. So we're going to need S and I, and adding them together is kind of nice, right? Because we see that when we increase the number of infected people, we're going to increase the rate of infection. Similarly, if we increase the number of susceptible people, we're going to increase the rate of infection. In this case, I'm going to argue that it's going to be S actually times I. And the reasoning here, and this is like up for debate, right? This is you could spin out a model with CPS plus I, and in fact, there's probably situations in which that makes more sense. But the argument here is basically that in this completely sort of random case where we just assume that people are, bumping into each other through Brownian motion or something like that, and every person has an equal probability of meeting every other person, then in theory, if we double the number of infected people, we would assume that the infection rate is also going to double. And similarly, if we double the number of susceptible people, we would assume that twice as many susceptible people run into an infected person. And so that also doubles. Now, of course, this only works in a purely theoretical world. But that's what I'm going to argue. Oh, I'm going to argue, and the SIR model argues we should use. So this is note. Multiplication here. Because increasing S or I by a factor of A should increase infections by a factor of A. Okay. Oh, sorry, not infections, infection rate. Okay, so any questions about that? And again, this is sort of based off the probabilistic reasoning that we've been working with up until now. But again, like it is not necessarily the case, right? That there are many different models you could propose. In some sense, this is just going to be the most basic one. Okay. So let's assume this. And now, let K be the expected value number of days to recover. So if we expect that you're sick for 10 days, for instance, then we would expect, roughly that 1 over 10 people are recovering every day, right? So if we expect number of days to recover, then we expect that I over K people recover each day. So di dt is going to be, okay, so by conservation of people, we're not killing anybody in the situation. By conservation of people, this should be everybody who becomes susceptible should be, so who's susceptible and who's being taken out of the susceptible pool needs to become sick. And then they recover in 1/k days. Right. Again, the idea here about the 1/k is that if it, say, takes 10 days to recover, then we would roughly expect that, you know, given that sick people are entering and exiting the system, that on any day, we would expect 1/10 people to recover. Okay. Are there any questions about that? Okay. So finally, we're going to have dr dt equals, well, okay, since this is a simple model, it's just going to be the recovered people are the people that stopped being sick. So 1/k times I. And we have the following equations. SIR equations. So this is going to be ds dt. I'm going to change variables slightly, but I'll write down what I mean by everything. Minus beta times is. Di dt is beta is minus gamma. And dr dt is gamma I, where here beta equals p times c, and gamma is 1/k. Just some terminology. Beta is called the force of, sorry, beta is the transmission coefficient. And beta I is called the force of infection. Okay. Any questions? Okay, so these are, of course, special cases of a much more general set of equations, where basically you can assume that these aren't constant and do all kinds of stuff. And it's quite fun playing around with these. And we'll look at an example in the homework of something more complicated. And we'll revisit these equations next week, and we'll use them to say something about, we'll do our first analysis of sort of phase space here. But you'll notice two things. Notice these equations are nonlinear. Or this system is nonlinear. Oh, it absolutely is. Thank you very much. Okay, yeah, thank you. So yeah, so the first thing is that the system is nonlinear, and what this means is that we don't know how to solve it. So we don't know how to solve it. It's actually worse than that, though. Not only do we not know how to solve it, but there isn't really a closed form solution. So you can certainly solve some nonlinear systems, but in general, even something this simple, there isn't really a closed form solution lying around. So what do we do? Well, there's two things we can do. So the first is we can simulate numerically, and we'll do that in a second. So what to do? So we can simulate, which we'll do in a second. Two, we can extract information from the equations. From the equations. And three, we can analyze its equilibrium behavior. I shouldn't say that, because we actually want to do something even more general. Sorry, we can analyze the solution behavior by carefully considering the derivatives. Solutions. Okay. So let me just do one last computation here, and then we can take a quick break. So what do we want here? So in the previous example, we saw that by looking at something like where the blood concentration was at a maximum, we actually can say useful things about how to find the parameters and fix the problem. In this case, there's something called the basic reproduction number. And so I would really say, so finding things like the basic reproduction number or that relationship that we talked about before with the derivatives is really important. And it's really important because for two reasons. One, if you can find sort of those kinds of simple quantitative relationships, like, oh yeah, the peak there, that's going to be the ratio of the absorption coefficients, then you can communicate that to somebody who's a layman. Second, they tend to give you actual like testable formula, right? You start off with this really complicated, with these simple assumptions, go through this really complicated differential equations process, and then you should get to some sort of testable, nice formula. And this is how these things are derived. The basic reproduction number is a really classic example of this, which actually, I mean, some of you may have heard this term tossed around in the last few months, but here's how you get it. So the basic reproduction number, I'm just going to call it the BRI. Oh, I don't know why I'm going to call it the BRI since that's not what it is. The BRN. It's the number of cases is number of new cases generated by a single infected person. A single infected person. Okay. So here, and basically anytime you write down a variation of the SIR model, you want to include the basic reproduction number. Any time. A disease number or disease model. Find the basic reproduction number. This is just, and the reason for this is the following. what happens if the basic reproduction number is, well, okay, so what happens if the basic reproduction number is greater than 0? I should actually say, I'm going to call it R. Sorry, it's not greater than 0, it's greater than 1. So again, the basic reproduction number is the number of people that we would expect a single person to infect, right? So if you've got one person in the population in the entire time that they're sick, how many people do they infect? And what if that number is greater than 1? Exactly. So the rate of people being infected is greater than the rate of recovery. And in particular, we have what's called an epidemic. So the number, so one person can infect more people than one person. And as a result, we would expect the number of infections to go up. Go. So this is the context in which you will have seen the basic reproduction number in the past few months. So how to compute it? 2 ways to compute. And there has been, in the last few months, a lot of ink and sweat and tears and blood spilled trying to figure out what the basic reproduction number of the current pandemic is in various places. Because, of course, it's going to wind up changing place to place. So 2 ways to compute. 1, we'll look at, so how many, so let's do this out quickly. So for S equals whatever the initial susceptible population is, I equals 1, we get beta times S nod times 1 new infections per day. Right? This is just the number of new infections we get, the rate of infection. This is going to happen, so the person is infected for 1 over gamma days. So R naught is going to be, so it's going to be 1 over gamma times this is going to be 1 over gamma times beta times S naught is equal to beta S naught over gamma. Great. That's the basic reproduction number. And importantly, notice that it depends on S naught. So if S naught, well, by setting this equal to 1, greater than 1, what are we going to have? We need S naught greater than gamma over beta. We have an epidemic. We have an outbreak. And so in particular, and this is interesting and important and kind of a non-trivial result of this model, it's, kind of the simplest thing we could write down. And what we see is actually the outbreaks can only occur if there's enough susceptible people around. That there's some sort of threshold where if we have enough susceptible people, then you can have an outbreak. And if you don't have enough susceptible people, then you can actually have recovery. And I know that I don't need to tell you guys this, but this is roughly the philosophy behind social distancing. This is also why the cities are doing a lot worse than the country right now. But okay. And in fact, what we'll see is that you can actually, if you're below this outbreak threshold, things will die off. So there's a second way you can get this, which is find where di dt is equal to 0. And here in this case, what's that going to be? So di dt is equal to 0. So we have 0 equals I prime is equal to beta is minus gamma I S equals S non equals 1, so with one infected person, and this is going to be, again, S non equals S non beta minus gamma equals 0, or S non beta over gamma equals R naught equals 1. So basically, the basic reproduction number shows up as an expression of when the infection rate is increasing or decreasing, exactly as we would expect. Okay, so thank you guys for sitting through now 2 hours and 10 minutes. Let's break really fast, and I just want to make sure that we have enough time to do everything. So can we reconvene at 3:15 my time? So it's currently 3:07, so it would be about an 8-minute break. Does anyone object to that? If you do, I'm more than happy to give a longer break. Okay, so let's reconvene at 3:15, and when we do, we will be jumping over to look at the lab. So bring that on up, or if you can't, feel free to ask me. Oh, this is critical town size. Yeah, so it's kind of a fun game that you can play right now where basically you take the SIR model and you stick it on a bunch of different cities or something. And so you have N cities as an example, then you have N SIR models, one on each one. And then you try to predict the coefficients for each one, and then you try to predict transfer between them or transfer between communities. That's what some of these epidemic models are based off of at the moment. I think the northeastern one is much more computational, but it's still a graph theory based network. But basically, you just wind up with instead of 3 equations, it's 3 times n equations, and it's kind of a fun little fun little game. I mean, it's quite complicated, of course. And I'm going to send out something on this. We'll send out a link to the Northeastern model, which is interesting. It's quite different than what we're looking at. But send out a link to the Northeastern model. And also, there's a great thing that 538 did on just how complicated it is to estimate beta and gamma. Actually, gamma is not too bad. We actually, we have some idea of what gamma is, but it turns out that beta is very, very, very hard to estimate. That's kind of where we are right now. All right, are there any questions? I'm more than happy to take questions while we are theoretically on break. Quick. Can you guys hear me? Okay, thank you. I just transferred my audio from one machine to another. We'll leave that over there since it's technically doing the streaming to YouTube. But, yeah. So again, I'm going to say about whatever we do in class here, and I'll say about whatever we do in class here, and I'll post it to the Canvas and to the Blackboard. Not to the Blackboard, so I'll post it to Colab as well. So if you want to look at it, you can. Okay, so let's get started again. So first, were there any quick question? Were there any questions that came up last time about collab in general that this would be a good that you'd be interested in asking before we get started on round 2? Okay. Well, hopefully you guys enjoyed it. So let's just have a quick review, right? So before we had things like autonomous differential equations, and so we're gonna, as usual, bring in our libraries, ODE and matplotlib for plotting, and NumPy for matrix handling, and everything else, all of our numerical functions and whatnot. And the way that we do things, so if we want to, for instance, solve a differential equation, then we set up a model. You can actually call this thing whatever you want. If you want to call it, cat or something. Oh, actually, yeah, be careful about calling it cat because that actually means something in Python. But you can even call it y of t if you, or f if you want to. But I like sticking with model. It's just a good reminder of what it is. So then what do we want to do? So model is supposed to give the derivative given t and y. And always remember that it's yt in this order, otherwise things will get wonky. It'll try to feed the y value into the first slot, no matter what. So here we have dy dt equals sine of y. Then, oh, can't do that. It'll yell at me. Return dy dt. And we can check, so model 0, 1, great. We get sine of y, which is 0. So as a quick thing, which some of you probably noticed, I'm actually doing this in 2 steps. Technically, if we wanted to, we could just return np of sine. It works just fine. In this case, do what you want. This is just for a little bit more clarity. Okay, so we define that, and then let's let under time range. So t is going to be, we can use linspace, yeah, between 0 and 10, say. Let's give ourselves 100 data points, and then our solution is going to be ODE int of model. Then I'm going to forget the syntax. Yeah. So for our y nod, 0.1, and then I want to feed it t, and it's going to yell at me. We don't pass it. We're not passing it any parameters, so we don't have to put the k in, or the args in. plt.plot t solution. Okay, and here we go. And if you remember, this is exactly what we expected to get, right? We expected that 0 was going to be an unstable equilibrium. And so things were going to go away from it, and they're going to go away from it up to about pi. And that's about where we are here, 3.14. And in fact, if we wanted to, we could, run this a couple of times. So say put this in as 0.1 at the moment. And let's throw in a negative value as well. Okay, and here we go. We start to see this branching up and branching down. And the kind of behavior that we predicted, if you go back to the notes a couple of days ago, when we were talking about autonomous differential equations, we said, oh yeah, actually this equation is going to have a bunch of equilibria, and we're going to have increasing, decreasing, increasing, decreasing solutions, just exactly like this. mean, in fact, if we want, we can use a for loop to say, let's look at a bunch of different solutions. In fact, let's look at np dot linspace. Let's look at all the solutions between, say, -10 and 10, and let's space them out. Let's look at 10. In. There we go. Exactly what we expected. And we see that these equilibrium lines that we're kind of going in towards are exactly at pi, 3 pi, minus 3 pi. Yeah, sorry, pi, 3 pi, minus 3 pi, minus pi, etc. Any questions? I mean, you could probably ramp this up to 100 if you want. Yeah, there we go. All kinds of fun. So you can see that as we start off very, very close to the unstable equilibrium, we do stay there longer, but eventually we always fall into the stable equilibrium. Oh, by the way, if you aren't able to type the code that I'm typing fast enough, you can feel free to request code, and I can just copy and paste it into the chat window like that. It's not hard. Not hard to do. So do feel free to request a code snippet if you need one. Okay. So this is basically what we just did here above. Just a little reminder. Okay, so this is all well and good, but we have moved on, and now we're thinking about systems of differential equations. And so we want to solve systems of differential equations, and luckily we can just use the same solver we did before. We can just use ODE and it can handle systems of differential equations, and it handles them seamlessly, actually, just using some linear algebra. So basically, it's going to work kind of exactly the way as you would expect. So ODE is going to, instead of taking a model that returns a single value for the derivative, it's now going to take a model that returns a list of values, an ordered list of values for the series of derivatives. So let's say that we have this example, right? So this is our standard circular example. So we have dx dt equals y of t, dy dt equals minus x of t. And we are going to write this in matrix form, as we're used to now. So x prime equals a list now of vectors, so a list of derivatives, and a list of expressions for those derivatives. And so we just want to do the same thing. So we are going to have a x of t now. In fact, we could call x y as well. Nothing has changed. It's just a slightly different name variable. But the x that we feed in now is going to be a list. And so there are two ways we can access it. But the simplest one is I'm just going to use a lowercase x for not vectored things and an uppercase x for vectored things. And then we just need to define dx dt and dy dt. And then we can combine them together into dx dt equals dx dt dy dt. So again, we're going to compute both of our derivatives. Then we're going to put them in a list. And then we'll return the list. dx dt. Okay, so what is our first derivative, dx dt, going to be in this case? Y, exactly.
and this will be minus x. And you know, I just realized I did a little trick here. I didn't say what this trick was. So this line here is this is something nice which Python will allow you to do. So let's say that I have a vector like p is 1, 3, 4, but I want to split 1, 3, and 4 off into their own variables. So I want a equals p, first element of p, and b equals the second element of p, and c equals the third element of p. So I can do all this. And here this is just p of 0. Oops. Recall is the first element, the second element, the third element. I can do this all this way. I can do it in one, or I can do it in one line just by saying, I've got a vector p, and I'm going to make a new vector with those variables inside it. And then there we go. And sure enough, in A, it is now stored 1, in B, it is stored 3, and in C, it is stored 4. And so that's what we're doing here. So we're expecting, does the order matter? Yes, because the order, that's a very good question. Yeah, because the order here is an assignment operator, right? So there's, in mathematics, there's actually like several different things that we mean by equals, and we kind of use them interchangeably. But in here, in Python, it's the equals of assignment. And the equals of assignment is always one way, right? You're taking the value in one thing and assigning it to the other. And so here, the equals of assignment is saying we're assigning the variables lowercase x and y, whatever we find in uppercase x. So similar, we could do the same thing here. So let's say that we have p equals CBA. And we've assigned p the values that were in CBA, which is slightly different, of course, as I reordered them. Thank you very much. It's a very good question. Because the other thing that equals is not, and this doesn't come up in Python because Python actually just circumvents this, but in a lot of programming languages, equals is not a truth relation either, right? So in mathematics, we say A equals B, and that can be true or false. When we write equals in programming, it's always the equals of assignment. Okay, so here we go. We've got our model. And so we want to actually run this now. And so here's a more condensed version, right? So we can leave the parentheses off. We can construct dx dt in one go, right? Here we've done it in 2 steps. We can do it in 1, and we can return things. And so now we just need to specify our initial conditions, specify our time, and let ODE run it. So let's specify our initial conditions. X is 0 and y is 1. T equal np dot space 0 to 10, I think should be good. And then our solution is going to be ODE int model x nod t. And what do we get out of this? So x solution now is an array, and it's an array of values, right? It's a 2 by 100 array, which we can figure out if we look at the shape. 100 by 2 array, sorry. It's a 100 by 2 array, and the left-hand column here, the 0th column, is going to be, so the column, so the left-hand column here is going to be the x values, and the right-hand column is going to be the y values. And we can access any element of that by, for instance, giving its index, just as we would for like matrix notation. So 0, 0, 0. You leave that open fast. So x sol 0, 1 is going to be 1. right? So the first index is going to be the vertical direction, the second index is going to be the horizontal direction, so or columns and rows respectively. But another thing we can do in Python is we can take what's called a slice. So let's say that we want the first 5 values in the second row. Well, we can say, let's take 0 to 5 in row 1, and here we go, it returns them. 1, these first 5 values in the second row. We can also then take all of the values in the second row by just using the pure slice operator, or actually just by leaving it blank. Oh, no, we can't, never mind. Okay, by using the pure slice operator. I think you can leave blank an R. Okay, any questions? Sorry. So what this means now is that if we want, we can plot these things. So we use plt.plot, and let's plot our 0th solution. And let's add a label and remind ourselves what this is. So this is going to be X. And there we go. And that's exactly what we expect, remember? We started off with our sort of first example of a system of a complex system of differential equations. We expect circles. We expect X to be in terms of sine and cosine, and here we go. We can also then plot the second one, call it Y. And what's the point of labeling things if we don't add a legend? Here we go. Here are our 2 solutions together. Any questions? Okay. What we're really interested in moving forward, though, is so I shouldn't say we're really interested. We're also really interested in these solutions, but often we're interested in understanding how the solutions relate to each other and viewing them in solution space. And so what that's going to look like, and yeah, we could add X labels and Y labels and do this out a little bit better. Add a title here. So versus no, okay, whatever. We want to plot them against each other. So if we plot X solution 0 versus X solution 1, then suddenly we get our concentric circles. Okay. Any questions? Okay, so now that we have this as well, though, we can take and modify this model to plot solutions for, like anything that we, that we've done by hand in class so far, right? So again, let's make t equals p dot space 0, 10, give it 100. Bobs, let's just make let's fix x naught of 1, 0 for the moment. And sol equals ODE and model not t. And I'm going to try something else. I'll try something here, and you can try your own favorite, right? The general form here is going to be ax plus by plus cx plus dy, right? So 3 times x minus 2 times y, 4 times x minus 1 y. Great, let's see what happens. Okay, here we go. So quick question. Are the solutions complex or real? or sorry, are the eigenvalues of the matrix here complex or real? Complex, exactly. And is the trace of the matrix greater than 0 or less than 0? So why do you say it's greater than 0, Anjali? I'll say you're correct. Why do you say it? Because it's unstable. Exactly. Right. We're starting off with an initial condition of 0, 1 right in there, and if you look at our axes here, without x ticks and y ticks on the axes, it could be going in or out, but we can see that we started off close to 0 and we're spiraling very rapidly outwards. You're exactly correct. Okay. Any questions? We can, of course, also, if we want to, for instance, try a bunch of different initial conditions, we can more and less complicated ways to do this. It can be a little bit hard to change them both at once, but we could do something like changing, so for x naught, for instance, in np dot space -1 to 1, and then solving it out with x naught 0. Oops. I certainly want to plot these. We get these fabulous spirals outwards. And yeah, it's 2 plus 2. So this is the other example we looked at in class of just a semi-stable instance. And I think actually what's going on here is I want to drop this down by 1. Well, no, that's still going way too fast. Yeah. So you can see these curves. What are we? Well, anyway, we can play around, or one can play around with these things a bit and try to. Yeah, okay, so this is an example then of that semi-stable behavior. -10, do we get a better picture? Yeah, anyway. So yeah, so I would encourage you to play around with this and look at these big solution spaces. And notice that this is like fast, right? Modern computers can solve ODEs incredibly quickly. And I mean, in fact, if you remember, there was this example that I kind of brought up, maybe a little bit over the break, of if we wanted to do something like simulate, 4 or 5 different cities, and put an SIR model in each city and put some sort of transfer between the cities and think about the behavior of that. I mean, it sounds like considered an impossibly complicated problem to do by hand. It's basically trivial to do using a computer until you get up in the realm of hundreds or thousands of such cities. It's completely doable. And so with the sort of the poking towards final projects, if anyone is interested in doing a sort of multi-city SIR model final project, that is definitely a viable option. And I haven't had somebody do one yet, which I've been a little disappointed by. So, okay, any questions? So I've sort of said all the things, and then I'm going to go down here and explain them. So we can look at some practice. So coupled linear systems. I'll leave that one again as practice, but let's quickly look at a couple of nonlinear systems here. So we can do a nonlinear system exactly the same way as we do a linear system, right? As far as the ODE solver doesn't know if the system's linear or not and does not care. So in this case, we're going to have our, let's just do dx dt in one call. So it'll be dx is going to be x, y equals x, y times x divided by 10 is y, and x minus x times y divided by 4. Return dx dy. And then we'll set t equal to np dot space 0, 10, 100 seems to be working. Set our initial conditions to be 1, 1. Solution is equal to ODE and model x naught t. And then let's plot x solution 0 versus x solution 1. And I forgot a comma here, I'm just going to break everything. That did not help. Dx dy is not defined. That is true. Plot is not defined because import is PLT. Okay, here we go. So this is kind of fun. It's it seems to be a sort of, so again, this is nonlinear, and we can see, you know, it's a kind of non-stable-ish closed orbit. And if we take a look at this, so if we want to plot multiple things, just as an aside, we can use subspaces. You can use the subspace call, and this will give us multiple axes that we can plot to, just like in MATLAB. So say 1, 3 as an example. Then call AX 0. So this then will return an array of axes. Plot different things to each one. 0, 1, and 2. And what this can be nice for is, for instance, if we want to look at multiple plots side by side. Subplots. Okay. And so we can see X, we can see Y, and we can see how they combine together. And we can use fig size to make this look a little bit nicer. Okay. So, I mean, I would really encourage you to dig into Matplotlib a little bit, because you have a huge amount of control over what you can do with making nice looking plots. For those of you that are Python whizzes already, you'll of course be saying, like, why are we using something nice like Seaborn? There are even nicer plotting mechanisms that you can use on top of this, but I definitely believe that Matplotlib has the most power, and it's also the simplest. It is not the prettiest, and there are much prettier things that you can do, but it's a good first tool. And if you're really interested in data representation and visualization, really the thing to look at is P5. That's probably for your art, kind of artistic data representation stuff. That's going to be the best. Okay, but you know, play around with our initial conditions here, see what happens, and you see these kind of interesting warbling. Oop, we fall off a cliff. Sort of some interesting warbling behaviors, and then solutions are going to get kind of interesting. We're seeing that they're becoming more angular. How close can we get to 4? And then something strange happens. Well, what happens is that one of our values is 0. And then we go above 4 and everything blows up horribly. So this is something you're going to have to get used to. Because again, Matplotlib is a numerical solver at the end of the day. And so if you have small precision errors can rapidly compound into basically gradient explosions. And if you see an error like this, all of a sudden you're not seeing what you expect, you zoomed way out, the thing's blown up. There's a couple of solutions. One, note that that is a part of parameter space that you shouldn't be going into and try to figure out why. Two, shorten your interval here. Okay, so what happened here actually was it was just genuinely exploding, right? It just gets really big, really fast, and if we shorten our interval, it's okay. Sometimes though, that's not really what's happening. And I don't think it is in this case, but if you increase your precision, yeah, it's not going to work in this case. Sometimes if you increase your precision, you can also stop gradient explosions if the explosion shouldn't be happening. Okay, any questions? So that's basically, oh yeah, so here we go. There's a guide to subplotting. And that basically is how you plot systems of equations or how you deal with systems of equations in ODE. And it's really no harder than dealing with a single one. And it's no harder dealing with 3 or 4. So for instance, if we wanted to solve a 4x4 system, all we need to do is assume that we're going to X, Y, Z, W, etc., X1, X2, X3, X4, and return a vector with 4 elements. So that said, there's a lot of playing around that can be done. If you have errors or questions, please do ask. Things can get transposed and screwed up, and you'll accidentally find yourself dumping huge quantities of solving 10,000 equations when you mess with one. But it should be relatively straightforward. So there's a couple of problems. Let's just take a look at. And here's a nice little biokinetic model. And so then here's what I want you to, so I would really like you to do this problem. I highly recommend it. So this case study in the influenza outbreak. And it'll show you, so especially those of you who don't have a lot of experience in Python but are interested in data science, this is going to be a bit of a first example of how to use data frames. But so this example, it's basically we want to actually test this SIR model that we've been talking about today, and that we'll talk a little bit more about next week. And we want to test it against some real data. And there was a famous case in a British boarding school where there was an influenza outbreak, and they had a closed environment, and they actually just tracked what happened with the influenza outbreak. And so I pulled the numbers for you guys and just stuck them in here. And I stuck them in an object called a data frame. So a data frame is something that it's kind of like a spreadsheet, but it's a big table where you can do things like label the columns and rows. And this is the most common thing to work with when you're sort of working in data science on the glorified spreadsheet, or I shouldn't say glorified spreadsheet makes it sound like a bad thing. It's sort of spreadsheet on steroids style of information. The data frames are very easy to define, so you define them with a little dictionary, and then you can construct them to a data frame. And then the fun thing about them is that you can call information from them. So for instance, by saying influenza, and then there's influenza, and then you can either call information, so if I want day, pull day out like that, or day. And what this means is that especially for sort of large unwieldy data sets, you can label things and recall things by labels, which is very nice. And so in this lab, so here's the picture, and this should remind you of the picture that I drew at the very beginning of class as to what this SIR curve looks like. And we'll talk about it as well next week a little bit. But I want you to take, I would really recommend that you take some time and take a look at this SIR model as matched to real world data. And in particular, part of what this does, and I'm more than happy to answer questions about this, even though it's not technically to be turned in, what I really want you to look at is problem 2 here. So basically, and there's a question, those of you who come from any sort of statistical background are probably wondering why we have not validated anything against data yet, or at all. And one of the reasons, as we'll see in this problem, is that dealing with confidence intervals is tricky with differential equations, because it turns out that when you start changing the parameters in a differential equation, even though the solution can be nice and smooth, the effect on the solution that those parameters has can be quite complicated and can wind up with having confidence intervals that sort of don't make sense in the way that we would like them to. Okay, so then finally, the homework actually begins. Homework here is going to be, as it was pointed out at the top of the lesson. These should be x prime, x1 prime, x2 prime, x1 prime, x2 prime, x1 prime, x2 prime. There are 2 labs, both of them have homework questions. Yeah, so that's a good question. Basically, what I did, is I split off. So basically, they both have the same homework questions. So I just split off something called problems, which is just lab 1, but I deleted everything above where it says homework. So what I would like you to do is do your actual homework on the problems one and then turn that in, just basically so that you don't, we don't have everybody turning in IPython notebooks that has all of this stuff at the top as well. But thank you for bringing that up. Oh, problem 3 is missing. Oh, that's good to know. Thank you. Thank you very much for letting me know that. I was not aware. I will get that fixed later this afternoon. To say a word about problem 3, what I really want you to, so problem 3 is kind of difficult to think about unless you just think about the trace determinant plane. And it's one of the things that's really useful about the trace determinant plane is that if you remember with the trace determinant plane, like we have like a strict like deterministic criteria for exactly what is going on with the solutions. And so I really just want you to, in problem 3, compute the eigenvalues, or not even give you the eigenvalues because you don't need to. So just use the trace and the determinant and figure out basically as you move A, how does this model move around the trace determinant plane? And what is that saying about the solutions? But if you have any questions, let me know. And then we get into the actual problem this time around, the big problem. So this is an extension of the SIR model, which is one of the reasons that I highly recommend that you do this example above. And it's going to be looking at the SIR model in the case of cholera. So in particular, the idea here is that the transfer mechanism isn't person to person. The transfer mechanism is slightly different. The transfer mechanism is that a person gets sick, then they transfer bacteria to the water supply, and then other people get sick from the water supply. So it's an indirect transfer. And, oh, I'm sorry, you can ignore this village 1, village 2, village 3 stuff. We're just going to use village 1. I had, yeah, I rewrote this problem slightly this time around because it didn't quite do what I wanted it to do. This is a more interesting version. So I will take you through how to set up these equations. And I would highly recommend you should look up these case studies in the book as well, because this is the book is talks about these and does some kind of different things I'm going to do here. And so what we're trying to look at again is we're going to analyze this new case in a kind of specific situation. And just like we did in the last homework, we really want to think about evaluating models a little bit. And so we want to figure out, so what are the global possible behaviors? And then we want to figure out if we are going to play around with some of these variables, which ones should we play around with in order to have the best effect, right? If you look at these variables, there's some that we can't play around with, right? So the total human population theoretically is fixed, rate of exposure, so that we can potentially play around with. Concentration of bacteria that leads to a 50% infection rate, well, that's just a fact of the matter, right? The recovery rate, that's just a fact of the matter. The growth and decay rate, that's just a fact of the matter. The rate of bacteria excretion per person, that we could potentially play around with, right? By trying to put in sanitation or hospitalization or things like that. So what you'll be doing is doing some analysis. Then you'll be computing the basic reproduction number. And finding the critical town size. So that's the town size at which an epidemic occurs. So then I want you to construct the phase plots for these parameters. Sorry, and by phase, I shouldn't say phase plots here. The solution curves for these parameters. Or no. Yeah. And then the final thing that we're going to do here is look at a slightly changed version of this model where we include a reinfection. And in this case, we want to figure out, it's going to turn out that there's a different number of equilibrium solutions for different values of the parameters. So here, how should we be? Edit this. So I may have to edit this question actually, because we didn't really get to talking about equilibrium solutions. But equilibrium solutions are going to be the star of the show next week. And equilibrium solutions are solutions where the derivative is 0. So I'll update this to find that. But basically, what we want to think about a little bit is how do the eigenvalues and eigenvectors, or sorry, how do the parameters change the number of constant solutions as we change the parameters around? It's kind of this whole problem is as we want to kind of understand as deeply as we can in a couple of different ways how these parameters are going to affect the kinds of solution curves we might have seen, in particular whether there's an epidemic or not. Okay. All right, are there any questions? All right, well, I will get this updated so that problem 3 is not missing off of the problem sheet. And if you have any questions, please post about it on Canvas. I will try to answer as soon as I can. And yeah, have a fabulous morning, afternoon, or evening, depending on where you are. And, yeah, I will see you next week, not before. Absolutely. Have a good one, everyone.